Hi guys. Okay, so let's start the remaining part of chapter 9, the solutions. So before we begin, I just want to do a little review of what we covered last time in the previous lecture, and that is related to the conversion factors. So we talked about the different types of concentrations, that is the mass by mass concentration, mass by mass percent, volume by volume percent, mass by volume percent, and the molarity. So these can be expressed as the conversion factors also. And what do they mean? So we talked about that 15% mass by mass percent means that there is 15 grams of whatever the solute is. So if it is an NaCl solution, so 15 grams of NaCl is in 100 grams of total solution. And the conversion factors then become 15 grams of NaCl over 100 grams of the solution, or 100 grams of the solutions over 15 grams of NaCl. Similarly, 10% volume by volume alcohol solution, that is going to mean 10 milliliters of alcohol is dissolved in 100 milliliters of the solution. And that is 10 milliliters of alcohol over 100 milliliters of the solution, or vice versa. Same story with the molarity, sorry, mass by volume. So 2% mass by volume percent means of any solution, or in this case, a sugar solution, it means that there is 2 grams of sugar dissolved in 100 milliliters of the solution. So the volume is in milliliters, the mass is in grams, the solute on top, the grams, the volume of the solution at the bottom, or vice versa. Those are the conversion factors. Then comes the molarity. Now the molarity, 2 molar HNO3 or any acid or any base or any solution. So if it is whatever the molarity is, this means moles of the solute over 1 liter of the solution. Okay, it's always 1 liter of the solution. And then, so 2 moles of the solute over 1 liter, it becomes the conversion factor, or 1 liter over 2 moles becomes the conversion factor. So this is what we discussed last time. And continuing on, from there, now we are beginning this chapter, the remaining part in this chapter, which is now we're going to use the concentrations as a conversion factor, different examples using the mass by volume percent to find the mass of a solute, the molarity to find the volume, then how we are going to use these conversion factors in the chemical reactions, then finding the volume of the reactant in a solution. Then we're going to look at dilutions, and then we're going to look at the properties of the solution. So we will first start with the vapor pressure lowering. This is going to be first. Second, we're going to take these two. So these two actually go by the, in the same, there's a formula for that. And the formula, we're going to use the formula, and there's a, that formula is not given. So I would say make note of that formula. Make note. In the handout, so you don't forget it, okay? And then the lowering of the vapor pressure. Now, osmosis and dialysis, I'm just going to do a general knowledge of it, just for you to understand what osmosis is. And however, we are for now leaving the calculations that are involving the osmolarity. So these problems, so if you want, you can do it on your own, but I don't want to. There's already so many calculations in this chapter that I just want to don't want to prolong it. There's no end to it. Okay, so now let's look at, first of all, these problems on page. So let's start this. First thing is the study check problem. Okay, this is 9.10, and that is on page 344. Page 344. Okay, here, what do we have? In 2010, the FDA approved 2.0% mass by volume. Okay, morphine oral solution. Morphine. Oral solution to treat severe or chronic pain. How many grams of morphine? So grams of morphine. How many grams of morphine does a patient receive if 0.60 milliliters of 2.0% mass by volume. Morphine solution was ordered. Okay, so we need to basically focus on these two. So 2.0% mass by volume solution is ordered, and that solution of that solution is 0.60 milliliters is ordered. So how many grams of morphine is one getting? So the solution to this problem lies in 2.0% mass by volume. What does this mean? So create a conversion factor of that. This means that 2.0 grams of morphine is present in 100 milliliters of solution. 100 milliliters of solution. Okay, or the other conversion factor is 100 milliliters of solution over 2.0 grams morphine. All right, so that's one piece. Next is, so we are given 0.60 milliliters of this solution, and we need to find out in this solution how many grams of morphine is present. Okay, and using the conversion factor. So which conversion factor will you use? The one that is 2.0 grams of morphine, because we need to find the morphine. So this stays in the numerator, and the denominator is the 100 milliliters of solution. Okay, and that gives you the grams of morphine. Okay, so here now we are going to do is 0.60 milliliters of solution times 2.0 grams morphine divided by 100 milliliters of solution. Okay, and that is giving you milliliters of solution. Milliliters of solution cancel out, and you're just left with the grams. So now you're going to do 0.60 times 2.0 divided by 100. So what do you get here? The answer is 0.012 grams of morphine. So it's always important to write the units, and it's always important to write in what context, you know, this is said. Okay, now we have the next problem is 9.11, study check. 9.11. So this is the second one. Okay, and here we have page 345. Page 345. Okay, so what is given here? How many milliliters of 6 molar HCl solution will provide 164 grams of HCl? So 6.0 molar HCl is given to us. We want 164 grams of HCl, and the question is how many milliliters? So how many milliliters of this solution of HCl? How many milliliters of the solution of HCl? Okay, so what are you going to do here? So first of all, always keep in mind, whenever the grams are given, the grams need to be converted always to moles. Okay, that's one thing. And next is, we are going to get the answer in liters. So liters need to be converted to milliliters. So always convert grams to moles, and that is using the molar mass. So we use the molar mass, convert grams to moles. Second thing is that whenever something is given in milliliters, we convert into liters using 1 liter over 1000 milliliters. and that gives you liters. Or when something is given you liters and you convert it into milliliters, then you multiply by 1000 milliliters over 1 liter, and you will get the answer in milliliters. Okay. So now what do you do here? You have 6 molar. So first of all, 6.0 m HCl. This means that 6.0 moles of HCl are present in 1 liter of solution, the acid solution, or 1 liter of the acid solution contains, okay, it contains 6.0 moles of HCl. All right. Now, what do you do here? You are taking this, sorry about that. During the daytime, so many phone calls. Anyway, so 164 grams of HCl. So convert that, 164 grams of HCl. Convert that to 1 mole. Convert that to the moles of HCl. And so what do we have here? The molar mass of HCl. Hydrogen is 1 grams, chlorine is 35 grams, and you get 36 grams of HCl. That's the molar mass of HCl. Okay, molar mass of HCl, 36 grams per mole. All right, so you put 36 grams of HCl, and here we see that the grams of HCl cancel out. Okay, so you are left with now 164 divided by 36, and you get, let me finish this. Okay, so we get 4.55 moles of HCl. Now we know the molarity is equal to moles over volume. And this volume is in liter, and that is of the solution. And the moles is of solute, and in this case, the solute is the HCl. And so if we need to find, and we need to find the volume. So volume is equal to moles over the molarity. Okay, volume is, so that is the formula you are going to use after doing the algebraic conversions. So volume is going to be in liters, moles is 4.55, and that is divided by the molarity is 6.0 molar. So this is the moles. Okay, and here you are going to get okay, let's finish this calculation. Okay, so this is 0.759 592, whatever this comes out to be. That is the volume in liters. But remember, the question is asking the answer in milliliters of HCl. So if the answer, if the question is asking, so convert the liters to milliliters, and you will have 0.759 milliliters times 1000 milliliters over 1 liter. So you see here, the liters and liters cancel out. And then when you multiply this, 0.759 times 1000, and this comes out to be 759.25. So the answer here is 759.25 milliliters. Okay, so the book is saying, the book answer is 750 milliliters. So that is like the, this is also, the closest choice you can say, closest choice in the molecular, in the multiple choice. When you get the multiple choice questions, so if this is the only choice you have, then you choose, then you pick the closest choice. So pick the closest choice in multiple in what is it called? Multiple choice questions. Multiple choice questions. Okay. So that's one thing. Now let's look at the chemical reactions in a solution. So here we are going to do the third one, which is the study check. 9.12, and this is page 346. All right, so here we have using the reaction in sample problem 9.12. Okay, the reaction is you are taking zinc as a solid, and that is reacting with 2 moles of HCl, and that is aqueous. That gives you H2, the hydrogen as a gas, and zinc fluoride, ZnCl2 aqueous. Okay, how many liters of, this is a reaction, and using the reaction, in this, how many grams of zinc can react? So we need to find the grams of zinc. How many grams of zinc can react with 225 milliliters? So volume is 225 milliliters of 0. Molarity is 0.200 m HCl solution. Okay, so you are given the molarity, you're given the volume, so you need to find a gram. So here's a stoichiometry problem. So here, what are you going to do? So first of all, you are going to find the moles of HCl. Okay. Also, you are going to convert the milliliters to liters. Okay, using moles is equal to molarity times volume. So this is the formula. Okay, which is basically just coming through the conversion of, when you have molarity is equal to moles over liters, volume in liters. Okay, so you take the volume in liters and times the moles, and that's just the algebraic conversion. So this is what you get. So this is one thing. Next is, as we talked about, that 1 liter over 1000 milliliters. So you're going to use this conversion factor to convert the milliliters to liters. Okay, so these are the two things you do. So next thing is once you find the moles of HCl, convert them to the moles of zinc. Okay, how do you do that? Using the mole to mole ratio. And that mole to mole ratio comes from the balanced equation. Okay, so that is the balanced, very important to see the balanced equation. And this balanced equation is this. All right, next is the third. Once you get the moles of zinc, convert them to the grams of zinc. And how do you do that? Using the molar mass of zinc. And for that, what will you do? You've already done that in your previous chapter, and that is you're going to look at the periodic table to get the molar mass. Okay, so these are the different steps that you are going to follow to solve this problem. Okay, let's do this now. So first is we are given the first convert 225 milliliters to liters. So first is 225 milliliters, convert that milliliters to liters. All right, so 225 milliliters times 1 liter over 1000 milliliters. So this gives you 0.225 liters. Next is we need to find the moles of HCl. So we are given 0.20 molarity. So moles of HCl is equal to 2.00. It's not 0.20, my mistake, sorry. Oh, it's 0.200, sorry, okay. 0.200 molarity times the volume. Volume is 0.225 liters. Okay, and so let's do the math. Okay, so this is 0.045 moles of HCl. Okay, next is you take the moles of HCl and you convert those moles of HCl to zincs of HCl using these coefficients, right? So we don't care about hydrogen, we don't care about zinc chloride. We only care about these two things, which is the relationship between zinc and HCl. So that is 1:2. So here we will get the moles of zinc. Moles of zinc. Okay, how do you get that? You take the moles of HCl, 0.045 moles of HCl. Multiply that by the molar ratio. So we see that 1 mole of zinc is reacting with 2 moles of HCl, and that is in the reaction right here. 2 to 1, okay, or 1 to 2. So now that means 0.05. So this rules out, or basically this cancels out the moles of HCl. Moles of HCl are canceled out. So 0.045 divide by 2 and you get 0.0225. So 0.0225 are the moles of zinc. Okay, now we have the moles of zinc. Okay, and you convert them to the grams of zinc using the molar mass of zinc. Okay, so 0.0225 moles of zinc times 1 mole of zinc. 1 mole of zinc, 65.41 is 65.41. You can just 0.41, or you can also use just 65 grams. That's fine. Grams of zinc. Okay, so that's why, you know, depending how exact you use the numbers from the periodic table, that also depends on how exact your answer is going to be. So anyways, 0.0225 times 65.41 divide by 1 and you get 1.47 grams of zinc. So always very important, please note, very important, after the numbers, please add the units and either the symbols or formula of the substance. So some of you are just, you know, thinking that like it's a math class. No, it's a chemistry class. You always need to do in what context you are using these. So, okay, so that's the answer from the book also. Okay, let's move on to the next one, which is volume of a reactant in a solution. So here is this one was 3 and this is the 4th. Now here you have the study check. (9.13), page 347, page 347. All right. So here you have for a reaction in a sample 9.13. So what reaction is here? So we are using Na2SO4. This is aqueous, soluble in water, okay, plus BaCl2. BaCl2 is aqueous, soluble in water, and this gives you BaSO4, and BaSO4 is solid, plus 2 moles of NaCl. 2 moles of NaCl is aqueous. All right, now you have sodium sulfate reacting with barium chloride gives you barium sulfate and sodium chloride. Okay, and this is always checked for balanced equation. Next is, so I'm going to, another thing is always checked. And then second is, all right, so here we have Na2SO4 with barium chloride. So for a reaction, how many milliliters? So you are going to find the volume in milliliters of 0.330 molar Na2SO4. Sodium sulfate solution is needed to react with 26, and then you have barium chloride solution is given to you, which is 0.216 molar, and 26. The volume of the barium chloride solution is 26.8 milliliters. Okay, so what is the volume of the sodium sulfate? So here, this is a strategy you're going to follow. So first, you are going to convert the milliliters to liters. Second, you are going to find the moles of barium chloride using the formula. Moles of barium chloride is equal to molarity times volume. Next, you are taking the moles of barium chloride and converting them to the moles of, let's do this here. Next is find the moles of Na2SO4. How? Using the mole to mole ratio. Okay. Next is, so it's something, same thing we've done. Next, you find the moles, you have the molarity. So next is find the volume of Na2SO4. How? Using the volume is equal to moles over the molarity. Okay, so this is the basic strategy. Okay, so first is, let's do this first, which is, so sorry about that white noise at the back. I'm sorry, 26.8 milliliters. So volume is 26.8 milliliters. So we convert that to liters by, so 26.8 milliliters times 1 liter, about 1000 milliliters. Okay, so you get 0.0268 liters. Okay, and this is the milliliters of BaCl2. Always in what context? So liters of BaCl2 solution. Okay, next is we converted and find the moles of BaCl2 is equal to molarity times the volume of BaCl2. So you're given the molarity of BaCl2 is 0.216. So 0.216 molar times the volume is now 0.0268 liters. And you get 0.00578 moles. And that is the moles of BaCl2. Okay, so moles of BaCl2, moles of BaCl2. Okay, next is you're going to convert the moles of BaCl2 to the moles of Na2SO4. So moles of Na2SO4 you find using the mole to mole ratio. Mole to mole ratio. Okay, mole to mole ratio. So what is that? So here it is 1-to-1 ratio. This is 1, this is 1, and generally, you know, this is when you balance it, so that comes up. So it's 1-to-1 ratio. So still I want to put it in the so 0.00578 moles of BaCl2 times 1 mole of Na2SO4 over 1 mole of BaCl2. So mole to mole ratio is coming from the balanced equation. So always in this case, it's 1-to-1. It could be different. Okay. So next is the, so the moles of Na2SO4 is 0.00578 moles. All right. Next is you take the moles. Next is find the volume of Na2SO4. So the volume of Na2SO4 is equal to the molarity, sorry, the moles over the volume. Okay, so the moles of Na2SO4 over the moles volume of Na2SO4 solution. No, sorry, molarity, not sorry, molarity. Molarity of Na2SO4 solution. Okay, so the volume of Na2SO4 is equal to the moles is 0.00578 moles divided by the molarity, and the given molarity in this case is 0.330. 0.330 molar Na2SO4. So let's see, what do you get? So 0.00578 divided by 0.330, and you get 0.0175 liters. Remember that, because molarity you have used, so the answer is going to be in liters. Okay, now the question is asking how many milliliters. So convert the liters to milliliters, and you have 0.0175 liters times 1000 milliliter over 1 liter, and you get 17.54 milliliters. 17.5 milliliters. That is enough. Okay, of Na2SO4 solution. Okay, so that is one piece. Now, next is we are going to look at the concept of dilution. So this one was 4, 5. Next is the concept of dilution. Now, what is dilution? Dilution is adding water. So dilution is not a chemical reaction. It is just a physical change. Okay, so it's just mixing of water, mixing with a very specific amount of water, mixing with a specific amount of water. Okay, so how much water are we going to add? We determine through the formula M1 V1 is equal to M2 V2. So what does this mean? This means that this side and this side, this means that this is a higher concentration solution. So the molarity is high, but the volume you're going to use is low. In this case, the molarity is low, but the volume that you're going to use is high. So in other words, this side is a higher concentrated solution, higher concentration, concentrated solution. And this side is a lower concentrated solution. So how is this solution of lower concentration prepared? So it is just a physical process. It's just a physical process. It's not a chemical reaction and not a chemical reaction. So in other words, you can recover the solute from the, you can recover the solute back by evaporation, basically. Okay, so here, or distillation. So here, how do we prepare this? So this is how you do. You take a solution of higher concentration that is in the labs, you know. So this is a bottle of a solution of higher concentration. Solution of higher concentration. So molarity is, so let us say this is 12 molar HCl, one example. So molarity is high, right? And we are going to take some amount of it is taken out and it is put in a Erlenmeyer flask. Now, because you are creating a solutions for a set of students coming in the lab, or you need it for your reactions, a solution which is not 12 molar, but you need, let us say, 6 molar of HCl, 6 molar HCl. All right. So you are going to take small amount. So this is the volume, but it is a less volume. And here you are creating, the molarity is low, but the volume is high. Larger. So you take this little amount with a small amount of higher, or a solution of higher concentration. It's a small amount of a solution of higher concentration. Is taken and then poured here, is taken and poured in an empty flask. After that, water is added. After that, water is added to whatever amount, to whatever, amount of you need. So now here we are going to take the water. Let's say it is coming from another source. So here's the water, and this water is taken out from here and poured here. And let us say you want to make a solution of, let us say, 250 milliliters. Okay, so you will fill the water only to this extent. So here's this water, and you're going to fill the water up till here. So when you took out, let us say, when you took this guy out from here, this is the HCl solution, and HCl, this is the HCl, and you took out some of the HCl and you poured it here, right? You poured it here. It's going to occupy some space, first of all. And then when you add water and then you mix it. So this is how this works. So this is the water. So some amount of water is added till it reaches the 250 ml, because you want the 250 ml. So you see a large concentration of a larger concentrated solution, when water is added, becomes less concentrated. So now we have a solution of lesser concentration. But larger volume. Okay, so this is what it is. So this is present in the stockroom. This is generally, stockrooms have it, or larger bottle, bottle that comes from the vendors. Okay, and this is what you prepare in the labs. Prepare in the labs. All right, now what will you do? Dilution. Nana, cut it out. Come here. Come here, baby. Nanu. Okay. I rescued a dog. I have a dog now. He's a very cute thing. So anyways, let's look at this. So study check. So here you have study check 9.14, and this is on page 350. Page 350. Okay, so here is the what initial volume of. So here's the question, that what is the initial volume of, So we need to find the volume of 15% mass by volume. Mannose solution is needed to prepare 125 milliliters of 3.0 mass by volume percent. Okay. So this is, one second, let's just do this here. So volume 1 is given, and that is the molarity given, or the concentration is 15% mass by volume. The other one is what you desire, what you need. So this is also, so this is a larger concentration, as you can see, larger concentration, and here is a lower concentration. And what is that lower concentration? The lower concentration is 3.0 mass, 3.0% mass by volume, and the volume you need is 125 milliliters. All right, so excuse me. Okay, so here's here's, in this case, it is okay to leave it in the milliliters. Okay, so we have the formula C1 V1 is equal to C2 V2. So let's call this C1 and let's call it V1, and this is C2 and this is V2. So we need to find V1. So what will you do? V1 is equal to C2 times V2 over C1. Okay, so we are going to now, next thing, leave V1 is equal to C2. C2 is 3.0% mass by volume, okay, times 125 milliliters, okay, over C1 was 15% mass by volume. So here, what do you get? Okay, so the volume is 25 milliliters of 15% mass by volume solution. So this is one thing, this is one problem. Study check 9.4. Next is, let's do 9.5. 9.5 study. So this one is 5, 6. Okay, so here, find the molarity of a diluted solution. So study check 9.15. Okay, All right, so here we will have, this one is on page 351, page 351. Okay, so what do you get here? You have what is the molarity of a solution? So you need to find the molarity of a solution when 50.0 milliliters of 4.00 molar KOH solution is diluted to is diluted to 200 milliliters. Okay, so here we are going to see M1 V1 is equal to M2 V2. Okay, so in ideal respect, you should convert milliliters to liters because molarity uses milliliters. So let's do that. So 50.0 milliliters times 1 liter over 1000 milliliters. And the next one is 200 milliliters times 1 liter over 1000 milliliters. So the answer here is 0.050 liters. And here the answer is 0.200 liters. Okay, so we have here M1 V1 is equal to M2 V2, right? So we will put here, we need to find a molarity. What is the molarity of a solution when? So this is 150. This is M1, sorry, this is V1, this is M1, this is V2, and we need to find M2. Okay, so V1 is given, M1 is given, V2 is given. So you need to find M2. Okay, so now, so M1 is 50, so sorry. So 0.05 M1, sorry. M1 is 4.00 molar times 0.050 liters, okay, is equal to M2. We need to find M2 times the V2 given is 0.200 liters. So 4.00 molar times 0.050 liters, divide that by 0.200 liters is equal to M2. Okay, so let me just bring this whole thing here. Okay, so here we just cut this off. So this was, and this is 550 ml. Okay, so when you do this thing, the rearrangement, M1 V1 over V2 is equal to M2. So that's the algebraic conversions. So you get this. Okay, now you have to do the math. Okay, so this comes out to be 1.0 molar KOH solution. Okay, of what molarity? Molarity we found out, and of 200 milliliters of 200.0, like exact 200 milliliters. Okay, so that's the molarity of this solution. All right, so this changes the next to the next part. After this, we will have this was 7 and then 8. Now here we are looking at the properties of solutions. So first is the general properties of solution. So first is just a general, that what exactly are the solutions? Then not everything is a solution. Then there's things that, you know, solutes when they mix, they can also form colloids, and then they can also form suspensions. So the whole thing here is the size of the solute particles. Okay, the size of the solute particles. So the solution, the particles, the solute particles, their size is very small, very, very small size of solute particles. Okay, so these colloids are larger. These are generally, these are small atoms, so small size of atoms and ions. Colloids are generally large molecules. And suspensions are very large particles, very, very large particles. So that's one thing. Next thing is that the solution is going to the light, like the effect of light, you know, the light, when the light passes, so the light passes through the solution, light passes through the solution. And so it becomes clear. It looks all clear, looks like all one. Okay, nothing is stopping the way of light. In the colloids, so colloids and the suspensions, these are big particles. So these, you know, they scatter the light. So when they scatter the light, then what happens? When the light is scattered, and that scattering of light is called Tyndall effect, Tyndall, Tyndall effect, the scattering of light. Okay. All right. So that's one piece. Next is the solute particles. So let's first look at the lowering of vapor pressure. Lowering of vapor pressure. So this is part A. Then comes here, lowering of vapor pressure. Lowering of vapor pressure. And with that said, we are going to also understand what is boiling. Okay, what is boiling? What is boiling? What do you call boiling? Okay, so here you have a clean solution. Okay, here you have absolutely, it's not even a solution, pure water. And here you have, let's make this. Okay, here you have okay. It's a beaker of water. Okay, and I'm going to just copy this and put it here. All right, so two scenarios. Okay, two scenarios. In one scenario, we are just boiling pure water. We are just boiling pure water. So this is one scenario where we are boiling the pure water. Another scenario, we are boiling a water in which there is a solute. So let's do this. Here's the pure water, absolutely nothing, all clean. And here's a pure water which has other suspended particles or some, you know, so let's just make these particles here. So there is a sodium chloride particles, you know, right here. Okay, so this is pure water, and here is water mixed with water plus salt, NaCl, or some other solute. Okay, anything, it could be anything, but generally for the sake of an example, you know. So here, in this case, the water, you put a thermometer here, you know, and then here also you put a thermometer. Okay, so here the temperature reading is 100 degrees Celsius is the boiling point. Boiling point. The boiling point is the temperature at which the water boils. And here the boiling point is, so let's just put this, I need more space actually. So let's say here 100 degrees Celsius is the boiling point. And here is going to be more than 100 degrees Celsius boiling point. And that more depends upon how much of the solute is there. Okay, it all depends on the solute. Remember that outside in the nature or in the environment, we have the atmosphere. Okay, so let's put this atmosphere, this color, clouds. Okay, so now we are trying to understand in an open system what's happening. Okay, now here we see that these clouds are exerting their pressure. The atmospheric pressure is there on the boiling solution. Okay, so we measure that atmospheric pressure. Our normal standard atmospheric pressure is 1 atm. Standard atmospheric pressure is 1 atm. Okay, now here when you boil the water, in the first case, when it is pure and clean and there's nothing, what happens is that the water immediately in the beginning, the bottom part gets hot. And so when it gets hot, we see bubbling, or in other words, liquid begins to convert to gas first. And as that happens, the water begins to rise, and it rises, and it rises, and these water droplets, like in the gas form, the water vapors. So water vapors in the gas form, vapors come and stick on the top, and we have seen that. But then after that, what happens? That when they stick on the top, they keep rising up. All these bubbles, they keep rising up. These are the bubbles. So when they rise up, they first stick to the top, and then afterwards, if you continue to provide heat, the heat is continuously provided. So that heat eventually converts the liquid water to the gaseous water, or in other words, the gaseous water vapor, they escape after they have gathered sufficient heat. So when they escape, they are escaping, but remember, they are still wet. So these water vapors are still wet. They cannot go any further. So that is why they're called water vapors. So they are wet and they are heavy, and so they remain on top, and they exert their own pressure called a vapor pressure, because they are all collected on the top. They are heavy, they are collected on the top, they cannot escape readily. Why? Because the atmospheric pressure is pushing them down. You see this? The atmospheric pressure is exerting a push on these water vapors to leave. So there is a little tug of war happening, you know. So here's these, oh God, sorry. Here is the outside atmospheric pressure forcing them to go back in, you know. And so this atmospheric pressure is pushing them to go out. So they don't readily agree to leave, you know. They keep on, they're getting, so they stay on the top. And when they stay on the top, that is called the pressure. They exert their own pressure weight because of their heaviness, right? So they are called these vapors. That's called a vapor pressure. But a time when vapor pressure, that is the vapor pressure of water, vapor pressure, the pressure, the force, the vapor pressure becomes equal to the atmospheric pressure. Then what happens? When it becomes equal to the atmospheric pressure, then the whole liquid boils. Then the whole liquid boils. And that happens at the temperature, at a certain temperature, when it has absorbed some amount of heat, and that temperature is called the boiling point. Okay, now that is the situation with the pure water. But the problem in the second case is that the liquid, water, and the solvent particles. So in the second case, the solvent particles come in the way. So solvent particles, the solute particles, my mistake here. So even though you have the bubbles forming, and that's fine, the bubbles will continue to form, and fine, the bubbles are going to rise, but something is going to come in between. That is these solute particles. Okay, so they are going to, same thing, they're going to happen. They're going to collect at the top, but these solvent particles are going to prevent them from leaving. So the solvent particles get in the way of the bubbles. So even though we will see some vapors, will leave slowly. So it's going to slow down. It's a slow process. So vapor pressure lesser, okay, is lesser vapor pressure. So let's write this down here, that when solute particles block the path of bubbles. What are bubbles? Bubbles are just gases. Okay, that is the water in the liquid state has converted to a gaseous state. That is just bubbles. So liquids or the solutions will take longer to boil. So solutions will take longer to boil. Okay, and when they take longer to boil, means that the boiling point will increase. Boiling point increases means that it's going to take more than 100 degrees temperature to boil. Okay, more than, boils at 100 degrees, because the vapor pressure has lowered. Here, the vapor pressure, remember, when the vapor pressure becomes equal to the atmospheric pressure, then the liquid boils. But when there are less vapors, then it is going to take longer for the liquid for the solution to boil. So vapor pressure is lowered due to the solute particles. All right, due to the solute particles. All right, now we have here lowering of vapor pressure. Okay, now we have, next part is the C part, which is, now we are going to look at here. There is depression. Because of that, there is a depression in freezing point. Okay, depression in freezing point. And there is elevation in boiling point. Okay, even before that, something that's I'm remembering is we need to here just get that piece out of the way. Okay, so here is the solute. Solute particles. Okay, so here keep that in mind, that at planes, in the planes, water boiling point is at 100 degrees Celsius. But as you move up, as you move up in higher up, so on the hills, the water's boiling point is less than 100 degrees Celsius, means water boils quickly. Water boils faster on the plains. Because why? On the hills, because lesser atmospheric pressure. So there's nothing pushing the vapors to escape. So remember, when the vapor pressure becomes equal to the atmospheric pressure. So if the atmospheric pressure is low, so a little bit of vapors is going to boil the liquid off. But on the hills, but on the beaches, you know, where the air is very thick, so the water's boiling point is going to be more than 100 degrees Celsius, because the water will boil. Water boils like slowly. You know, it will take longer because the atmospheric pressure is high. So that means you need a lot of vapors, you know. So based on this, we have designed, you know, the pressure cookers, and, you know, the pressure cookers are designed based on autoclaves and pressure cookers. All these are designed based on that. So let me write this down: autoclaves and pressure cookers. So if you are heating, are designed on this premise. Okay, so the more the pressure is, the more the outside pressure is, the longer it is going to take for a liquid or a solution to boil. Okay, next let's look at the depression in the freezing point. Now here you're going to use two formulas. One is delta TB is equal to I dot KB dot M dash. Just do like that. The other one is delta TF is equal to I times KF times M dash. Okay. Now here is the, this is the boiling point, and this one is the depression and freezing point. So these two equations. So this one and this one. So what are their meanings? Here, delta TB is change in boiling point. So we understand that, yes, if there are solute particles, the boiling point is going to change, but by how much? So that's what we figure out from these problems. So delta TB is change in boiling point, and delta TF, similarly, the freezing points are also lower. Water freezes at 0, but the water freezes at 0. So when you add something to it, it's going to be freezing lower than 0 now. It is going to take longer for it to freeze. Okay, so delta TF is the change in freezing point, change in freezing point. Okay, now KB is the EBULO, EBULIOSCO, ebuloscopic constants. Okay, specific to the solvent. So whatever the solvent you have, water or any oil or whatever that. So KB and KF. So it's that, it means that. So K stands for, K is that. Okay. Next is the value of I. I is the number of moles. Okay. For ionic compounds. For ionic compounds, that is when you have metals, non-metals, and metalloids. So metals, non-metals, and metalloids, or even non-metals non-metals and the metals, non-metals, and the polyatomic ions. Okay, and I is equal to 1 for molecular compounds. And generally, molecular compounds are those that contain lots of carbon and hydrogen bonds, lots of them. Okay, when carbon and hydrogen bonds are a lot, then that's it. Now, what is M dash? M dash stands for molality, MOLALITY, molality. Okay, molality is, what is a molality? Molality is the moles of the solute over the kilograms of the solvent. moles of the solute over the kilograms of the solvent. Kilograms of the solvent. All right. Now we will have now let's do some of these problems that relate to this. So here is in northern United States, the freezing temperature of calcium chloride. So first of all, let's look at the values of I. I don't want to like this, do this. I is equal to, like, for example, if you're adding NaCl, so the value of I is 2. If you have, like, for example, MgBr2, then this is 3. So 2 means 1 of sodium and 1 of chloride. This would means 1 of magnesium and 2 of bromines. Okay, minus 1. If you have aluminum, sorry, let's not do this. 4 of them. So you have, let's say, lead, calcium carbon, no, calcium, yeah, calcium phosphate. So this would mean there are 3 calciums with +2 charge, and you have 2 phosphate with -3 charge. So 3 + 2 becomes 5. So that's the value of I in that case. Okay, and then if you have, like, for example, AlOH whole thrice. So this is 4, which means 1 of aluminum with +3 charge and 3 of hydroxides with -1 charge. All right, so this is the way you get the value of I. So now the value of Kb, boiling point of, that's the freezing point they've given you, changes in the boiling point for water. Yeah, Kb for water. Kb, that's the ebullioscopic constant of water, is equal to 0. Is 0.5. Excuse me. Okay, so here we have 0.52 degrees Celsius kilograms per mole. Okay, and the value of Kf for water is equal to -1.86 degrees Celsius kilograms per mole. Okay, so now let's do this problem. This is a study check. And I'm going to do it because the way they have done it in the book is like a little bit confusing. So I'm doing not just a study check, actually. Or let's just do the study check. Okay, ethylene glycol, let's do this first. This is 9.16. 9.16, page 356. Page 356. Okay, so here you have ethylene glycol. Ethylene glycol is C2H6O2. C2H6O2. It is a non-electrolyte. So for the non-electrolytes, the value of I is equal to 1. Okay, is added to water. So we are looking at water as a solvent. So these values are going to be given to you. Okay, the value of KBs and the other ones, okay, will be given. So don't worry about that. Okay, is given in a radiator to give a solution containing 0.75 moles, okay, of ethylene glycol in 1 kilogram of water as a solvent. So when we talk about molality, this is what we mean. 0.75 moles of glycol ethylene glycol divided by 1 kilogram of water as a solvent. Okay. What is the boiling point of the solution? So find the boiling point. Find the boiling point. Okay, so here also, when we talk about the delta KB, the delta TB, so change in boiling point means the temperature final minus the temperature initial is equal to delta TB. So same is the case here. The final temperature of the final freezing point, final minus the initial. F stands for final and I stands for initial. Okay, now we have this TB is equal to, so find the value of TB. So delta TB is equal to I times KB times M dash. So I is 1 times the value of KB. So 1 mole times, so here, this is 1 mole times KB value is 0.52 degrees Celsius times kg over per mole. Okay, times the molarity. Okay, I have to just make this small. Okay. Sorry about that crowing at the back. It's very noisy, but you know what to do. Okay, anyway, so here you have 1 mole of the glycol. And then this is the value of KB for water and times the molality. And the molality is 0.75 moles of glycol divided by 1 kilograms of water as a solvent. Okay, so now let's get these removed. So, so moles and moles cancel out, kilograms and kilograms cancel out, and this also moles. Actually, that 1 mole, and then actually this is, you don't have to necessarily write it as mole, but that is what it means. That's a value of I. So I is 1, the value of I. Okay. All right. So, and this is the value of molality. And so let me just put it here, I for glycol. Okay. So now we have 1 times 0.52 times 0.75. And so what do we get here? So this is coming out to be delta TB is equal to negative 0.39 degrees Celsius. Okay, now pay attention. We need the final temperature. What is the boiling point? So we will have that is the final temperature. So delta TB is equal to T final minus T initial. So here we have T final is, we need to find what happens when you add this glycol to it. The initial temperature of water is 100 degrees Celsius. So always remember that the initial temperature of water is equal to 100 degrees Celsius. Okay, so that is the TB. So TB, we need to find for the temperature of this. Yeah, delta TB is coming out to be 0. It's not negative, 0.3. Okay, so delta TB plus 100 degrees Celsius is equal to T final. Simple math. Okay, so 0.39 degrees Celsius plus 100 degrees Celsius is equal to T final. So the T final comes out to be, T final is equal to 100.39 degrees Celsius, and that's the answer. Okay, so I've done this one, and then like I said, if you use this formula, you are going to get the, if you use this formula, then you are going to get the answer for the T final also for the problem that is given, the work example. So don't just copy it the way they have given you. Use this formula. It's very easy, not that hard. So that thing for your work example, but we need to wrap up also. So we have now, we've done 7 and then 8. Now I'm going to just finish this off quickly. This is the 8. This is the osmosis and dilution. Osmosis and dilution. Okay, sorry, not the dilution. It's the osmosis and dialysis. Okay, so on osmosis, what do you get? Osmosis is, look at this here. If you have a carrot that is like badly shriveled carrot, so you've seen it in your real life also, you take this carrot and you put this in a container of water. And here you see after some time, the carrot plumps up. So there is water, less water inside the carrot, but more water outside the carrot. So all this water, so the concentration of water is more outside, but the concentration of water is less inside. So this is a law of nature. Things flow from a higher concentration to a lower concentration. So your carrot, after some time, with our experience in life, is that the carrot we see gets plumped up. Okay, so here's the, right, let me write this down. So shriveled carrot gets swollen or plumped. Okay, when water flows, water from outside flows inside. Okay, inside the carrot. So lower concentration of water, inside, higher concentration of water outside, higher concentration of water outside. So how does the water flow? The water flows through these little holes in these membranes. And what are these? This is called the semi-permeable membrane. So this is the semi-permeable membrane. So what does the semi-permeable membrane do? The semi-permeable membrane allows the flow of only the water particles and nothing else. So the flow of water through the semi-permeable membrane, through the semi-permeable membrane. The flow of water through the semi-permeable membrane from higher concentration to lower concentration, and that is called the process of osmosis. Okay, that is the osmosis. Okay, so I'm running out of time here also. So what we're doing here now is we can leave some of this other stuff. You are welcome to read it. So based on this, dialysis is basically, now we figured this out. So through a membrane, now we can also filter, like ions. You can also filter some molecules, like small molecules like urea, uric acid, urea, So, and so they designed these are manufactured. These are manufactured, and these manufactured membranes only allow the flow or filtration of these ions from through, water, but not the blood, So, okay, so we are going to hear now. I'm going to just ask you to leave because we really don't have the time. I don't have the time now. So we are going to leave the osmotic pressure. Osmotic pressure. So this is the 356 page. 356, 357, okay, and 358, sorry, 358, and dialysis we've done 359. So like I said initially, that you need to only know the knowledge for this osmosis and the dialysis, but you can, so I said you can leave it from 356, 356, 357, 358, and 359. Okay, so all of these extra problems that are related to that. Okay, guys, if you have any questions, you can always ask me. Thank you for watching. Bye-bye.